Okay, welcome to class. This is Wednesday, September 23rd. Just making sure everybody's getting in the room. Shakira just joined. Gabe just joined. Okay, welcome. Today we're gonna do some other example of vectors and vector notation. And what I did as a vector example in our last session was very relevant to the homework problem, the written homework problem you're preparing for next week. And I'm going to do another example like it. What you need to know about vectors is simply, it's just a different way of talking about motion, about distance and length. It's a different way to use a right triangle. Since the idea of vector is used in so many different places, physical sciences, mechanical sciences, practical applications, it's got old and special terminology, that seems sometimes to be a little bit cumbersome. But I want to show you that terminology so you learn to speak it and read it correctly. Because if someone's trying to communicate something to you in writing, you have to understand what they're writing. But I always want you to think in the back of your mind, a vector is about a right triangle. And if I can draw the vector and see the right triangle, then I can assemble the pieces that I need. Okay, so what else are we working on here? You submitted a written assignment last night. I'm still reading through those. In a couple of places, I saw this idea, and in a couple of questions, you asked me about the XYZ homework. You would ask me sometimes several questions like, the homework says that the answer is 37.5, and I think the answer is 37.3, or something like that. And I can check those out. You send anything to me like that you have. But usually what happens, if you differed slightly, it means you rounded off too early. You rounded off in an intermediate step instead of the final step. So just a suggestion, use the exact values throughout your calculations. Only round off at the very end when you're presenting an answer. And so I'm going to illustrate that with the first example I do today. Brings Mason into the room. And when I say always use the exact values throughout the calculations, that doesn't mean you're writing down lots of numbers necessarily or recopying them. Remember, your calculator keeps track of as many digits as can fit inside it on any calculation. So what I don't want you to do, what you got to get out of the habit of doing is writing down what's written on your calculator, stopping after a couple digits, and then for your next calculation, using those couple digits you wrote down. Use all the digits from the calculator. Writing down those few digits in a preliminary way might be helpful for you to organize and understand what you're seeing, but it's kind of extra work that's interfering in your answer. I don't think it's bad extra work. I think it's extra work that helps you see what you're doing. But do not use approximations midway through the calculations of a problem. Approximations are what you report to the person who asked you the question if an approximation is appropriate. You can't just always round off on the way to the answer, or else you just get an answer that's slightly off its best truth. Okay, so let's go through a couple things in this picture here, and then we'll jump into a sample problem. So I want to get you used to the old style vector notation. And that is a vector is a line segment with an arrow head on one side. And the fancy language for that is a directed line segment. It's a line segment with a direction. This arrow is going upright and not down and left. You can name a vector with a single letter, like call this vector vector v. Or if you have 2 points, you can name a vector as you did a line segment. You could just call it the vector AB. But when you write the vector AB, it's really important that you obey the order. This vector started at A and ended at B, and that's why we go from left to right, A to B, and put the little vector hat on top. If you drew a vector between those 2 points, but you made it go from B to A, then you would have to name that vector differently. These 2 vectors, the red one and the black one, are different because they're going in different directions. Although the book does not always do this, because the book has the advantage of being able to write in boldface, and that's not as easy for us to do on paper. Always, always put an arrow hat, an arrow on the top of a vector, because that tells everyone that that thing you're writing down is a vector. Okay. Next convention. Bringing people in. Still, here's the next rule you have to understand. A vector has a length and a direction, but when you're talking about the length of a vector, you put these little vertical bars on there, absolute value bars if you like. Now, it's not absolute value as in the absolute value of 4 is 4 and the absolute value of -2 is 2. This absolute value bar stands for magnitude or length of a vector. And the fancy word is magnitude, the way you understand magnitude to mean size. And some people casually say length, and that's okay, as long as you understand that length could be things other than feet or inches. Length, in the example I'll show you later, could be miles per hour. The length of a vector, the magnitude of a vector, just means what's its size. Okay, next step. If I have a vector, let's call it W, on this diagonal right here, you can always break a vector up into its horizontal component and its vertical component. So if I take one vector and add the other vector, tail to head, head to tail, then the horizontal piece plus the vertical piece makes up the whole vector. And when I do that and call the horizontal and vertical pieces vectors, these horizontal and vertical pieces are called vector components. They are vectors themselves. And out of respect for horizontal and vertical, although I see I write this maybe small on my camera, you put a little subscript X. I'll try to write larger, for horizontal component, and a little subscript Y for vertical component. But do you see the transition? Now we're going to talk about a right triangle. So how does this mesh with right triangles? If I only want to consider the lengths, here's a vector with a length, magnitude of W. And here are the vector components, but I'm only interested in their length, 5 feet or 3 miles per hour. So if I slap magnitude bars on everybody, if I'm only talking about their lengths and not their directions, these are called the scalar components of the vector, the constant components of the vector, the magnitude components of the vector. Scalar is just a very old word that means scaling. 2 times 3 is 6. If you double 3, you get 6. If you scale something, like you talk about the scale on a map, 1 inch is 1,000 feet. So when you're only talking about the length, you slap length bars on all these 3, then you're talking about scalar components. If I'm talking about a right triangle and someone gives me an angle and someone says these 2 sides are A and B, I could just as easily call those sides A and B. Again, I'll make my diagrams larger. I apologize. But if someone throws this fancy notation at you, absolute value WX vector, just understand that they mean the length of that side. Absolute value WY vector means the length of that vertical side. And you tolerate this old style of writing, basically, because that's the way everybody writes in sciences and applications. And so you have to be like conversant with them. You have to speak the same language they speak. If you just think about these as sides of a triangle, that's how we're going to proceed. So this is my little warning here in green. And then I'll show you this next diagram. Vectors have their own special notation and terminology, but you control them and manage them just like right triangles. You can do everything you need to do if you just use your right triangle trigonometry. You can use a sine, cosine, secant, tangent, cotangent, cosecant. You can use all the 6 ratios that you can form. You might just write it a little differently. Okay, here's the last thing I want to say in this. Bring someone else in. There you go. Here's the last thing I want to say about just vector orientation or getting you used to vectors. If you have 2 vectors like u and v, you add them head to tail. Like u plus v means you take a copy of u and you lay it on the end point of v. You add head to tail, and you think of this as another copy of u. So if you go from v plus u, you get this u plus v here. Or if you go u plus v, you get u plus v. So people call this the parallelogram law. If you write any 2 vectors on a piece of paper and then copy them over again to make a parallelogram, 2 parallel sides, then the sum of the 2 vectors goes from their common tails to their common heads. You add vectors head to tail. Now that's one diagonal in the parallelogram. The other diagonal is also legitimate and useful. The other diagonal is the subtraction of the 2 vectors. And the only problem with the subtraction of 2 vectors is you got to make sure you put the arrowhead on the right end. Because u plus v and v plus u is going to be the same either way. But if you say u minus v and v minus u, those are 2 different directions. It matters whether you subtract or add in different order. 3 minus 5 or 5 minus 3, they're different. 3 plus 5, 5 plus 3, they're the same. So here's how you tell if you do the arrowhead on the right piece. Notice, how do you remember the direction of u plus v? You go head to tail. If you do v and then you add u minus v, what should you get? U minus v plus v. Since the v's would cancel out, it better be u. So I trace this diagram. V plus u minus v, is that the same as this side u? Head to tail, yes it is. So you can check that I have this u minus v, this red arrowhead here in the right place, by saying, is v plus u minus v truly equal to u in the diagram? Okay, So here's what I'm going to do. Let's throw this at a real problem. And again, this will be a little bit similar to the one you're doing for written homework. And I'm looking at a problem like 15 in section 2.5. And it's a word problem, and it's got a lot of words, and it's got no diagram. So let's get the words on the screen. And then I'll bring you in here. And then we'll just write down the work on the paper. So I'm just going into our homework system so I can see the book. And then I'll show you the problem. You may already have the book with you. Okay, we're checking this out. We're checking out the book. And I want to run over to section 2.5, number 15. The homework system, XYZ homework and XYZ textbooks are the same. You can use your same username and login at both. But sometimes it prompts you to re-log in. So that's a small distraction. So I'll get the item here on the screen, and then I'll open the screen for you. So let me share my screen. Okay, got it. I'm looking at 15. The reason I picked 15 is I want to show you that magnitude doesn't always mean length as in miles or inches or feet. Let's read it together, and then let's draw it. Airplane is headed north 30 degrees east and is traveling 200 miles per hour through the air. The air currents, though, are moving at a constant speed of 30 miles per hour in the direction north 60 degrees west. Now the air is going to blow the plane, the wind's going to blow the plane slightly off course, for which the pilots compensate. So what would be the true course of the plane in this case? So find its speed relative to the ground in miles per hour and find its direction relative to the ground and use 3 significant digits. So what I'm going to do here, I'm going to bring this back to my paper, but I will keep this problem written on part of the screen just in case I have to pop back to it. Let me pull out of there. On paper, got it. And let's make a rough drawing before we proceed. Manage my paper there, excuse me. So the idea, north 30 degrees east, that's the way the plane is going. You could call this 30 degrees east of north. That means if this is north, I'm heading north like that. This is east and west and south. I'm heading 30 degrees east of north. Now this is only a tiny drawing. I want to get used to it. Then I'll make a nice full-size drawing. And I'm going so fast, or at least the engines tell me I'm going so fast. And then what happens beyond that? I don't think I left myself enough room to draw this. The wind is blowing north 60 degrees west. So what's north 60 degrees west? or people call it 60 degrees west of north. North is the base. So that means from the north, again, from the vertical, I'm going 60 degrees to the west. That's over here. So I'm flying the plane in this direction, but the wind is blowing me in that direction. I'm going to be pushed a little bit farther north. So what is the net result when I add this vector of the plane speed plus this vector of the wind speed? What's the final vector? Now, the only thing I want to do to make a nice, accurate drawing now is write down the magnitudes. The plane is traveling 200 miles per hour. The wind is blowing 30 miles per hour. Now, just in rough drawing, these are like 7 times 30 is 210. So this vector, that's plane speed, is about 7 times as large, about slightly less than 7 times as large as the wind speed. So now I'm going to take that into account and draw a really nice picture. I have almost the mind that I should draw this picture in pencil in case I screw up with something I have to erase. Maybe I should do that. Maybe I'll do that. So here's, and I have to darken that, so I will darken that. But here's a nice line to the north. I'll trace over that. And here's the starting place of my plane. And I want to go 30 degrees east of north. So I'm just going to eyeball that. And I'm going to call this 200 miles per hour long. I'm going to darken this up with a pen, but I just want to make a fair drawing sketch with a pencil first. Now the wind is blowing me 60 degrees west of north. So I'm got this angle, which is 30. And now I got this angle. Now remember, this is the north again, true north. And 60 degrees west of north might look about like that. But the wind is not so great in size as the plane speed, right? I said that the plane speed was about 7 times as large. Now, I'm not going to make a perfect 7-to-1 ratio here, but let's call this the wind speed vector. And that's about 1/7 of this long vector. Not exactly, but let's call it that. Let's call the vector of the plane's motion P vector, P for plane. Let's call the motion of the wind W, W for wind. Sometimes you name things to help you remind what they stand for. And now let's draw it very neatly. So I'm going to make a dotted line here to represent north. I make a dotted line here to represent north. But then the plane vector is, sorry, I'm going to make it in black. 200 miles per hour long, 30 degrees east of north. Now you say 200 miles per hour long. What do you mean miles per hour long? Well, that's why I'm going to use that word magnitude. The magnitude of this is 200 miles per hour, not 200 miles, 200 miles per hour. So this is the vector P And the vector P has a magnitude of 200 miles per hour. Now this shorter wind vector heading over here, that is 60 degrees from the north. Plane vector was 30 degrees east of north. This is 60 degrees west of north. And now what I want is what happens when I add these two vectors. That'll be the true direction and speed of the plane. Do you see the vector I just drew right now is a little bit longer than the plane's actual speed? As it happens, because the wind is blowing, it's actually making the plane go faster. The wind is not fighting the plane. The wind's actually making the plane go a little bit faster. Now let's check this out and see how we're going to do this. What I have right here are two triangles. Let me enlarge the wind triangle. There's the wind triangle with its vector like that. This is W. And I would like to know, I know how long W is, 30 miles per hour, but I would like to know how long the horizontal and vertical components of W are. The vertical component of W, how long is that? The horizontal component of W, how long is that? Let me enlarge the plane's motion. There's a right triangle right there. I enlarge the plane's motion. Pull this triangle outside here and look at it. And I know that the length or the magnitude of the plane's motion is 200 miles per hour. But I would like to know how long this horizontal component is and how long this vertical component is. Once I know those, I can add them to find this last vector that says P plus W, plane plus wind. Why is that? Because the vertical component of the plane's motion, speed, plus the vertical component of the wind speed, those two things, the big thing and the little thing right here, will add up to the vertical component of the final speed of the plane. So that's actually getting longer. However, what about the horizontal component? I got the horizontal component of the plane going far over to the right, but the wind is blowing it back to the left. So in the end, I've got the plane going to the right and the wind blowing it back to the left. This means that the horizontal component of the true motion is going to be right here. And to find that, I'm going to subtract the long horizontal part minus the short horizontal part. So I need to find these horizontal and vertical components of these two vectors. And that's a way, kind of why I need this crazy names, just to keep all the players straight. I know the magnitude of the wind is 30 miles per hour. So now let's assign some angles. For the plane, this is 30 degrees from the vertical, but that also means that this angle is 30 degrees because these are matching angles here. So this is a 30 degree, 60 degree, 90-degree right triangle. I also get the same thing here. This angle is 60 degrees, and this angle is 30 degrees. The 30, 60, 90 triangles, these are special triangles, right? These are special triangles, and I know the ratio of them by heart, but I will use the calculator here just to practice showing you how to use the calculator and round off. So let's find WX, WY, PX, and PY. And then we'll assemble them together to find the true speed and direction of the plane. So I'll start down here from this triangle. At 30 degrees, WX is the adjacent side and the hypotenuse is 30 miles per hour. So I can say WX magnitude over 30 miles per hour is the what? Cosine of 30. Cosine of 30 degrees. And that means the WX magnitude is 30 miles per hour times the cosine of 30 degrees. That's what this is exactly. Now, what is that approximately? With a little wiggle on top. Let's pull out the calculator. Bring in my other calculator today because I just want to try this. I thought the black face would get a little more resolution if I wanted to show you close up what some of these buttons say. So I'm going to type in and make sure I'm in degrees. These is smaller print right here. But do you see on the fourth line, radians and degrees? It looks like right now this calculator is in radian mode. So I'm going to hop down there and go to degree mode. Okay, that's better. And I can quit. So what's 30 times cosine of 30 degrees? Calculator says 2598076211. I am not going to write down all those numbers. In fact, in some way, I don't even want to write down any of them. But just to help myself for reference, I'm going to say 259807. Okay, let's do WY the same way. WY is the opposite side to 30 degrees. I could use 60 degrees too, but the opposite side of 30 degrees. So WY divided by 30, opposite of 30 degrees divided by the length of the hypotenuse 30, going to give me the sine of 30 degrees. And that means that WY, always put the little arrow hat on it, is 30 miles per hour times the sine of 30 degrees. I'll enter that on the calculator and just make a note of it. 30 times sine 30 degrees. That's exactly 15, apparently. Now, if you know your 30, 60, 90 triangles, you know why that's exactly 15. I'll point that out, but just really write down 15. So it's exactly 30 sine 30 degrees, but that's exactly 15 miles per hour. Because why? In a 30, 60, 90 triangle, the short side, this will be the short side, is half the long side, half the hypotenuse. The short leg is half of the hypotenuse, half of 30 is 15. Okay, good. Now I know what this is approximately, be careful, 25, 9, 8, and several digits. I know what, this one is the 15. This one right here is the 25.98. I went off screen. So I know what those two links are. Now let's find the other two links, px and py. So I'm going to come down to this triangle. I see in my internet service a little bit of a lag. Now the recording should still be in good shape, but if you see it kind of blur out or slow, or if you're not hearing my voice nicely, you can let me know. You can type it in the chat window. But I do see a small lag in the service right now. Okay, let's look at 60 degrees. Px is adjacent, P magnitude is hypotenuse. So the adjacent side divided by the hypotenuse is cosine of 60. But the hypotenuse length is 200. So that makes this length 200 times the cosine of 60 degrees. Now I could type that into my calculator, but I could also use my 30, 60, 90 knowledge, right? 30, 60, 90 triangle, hypotenuse 200, short leg is half of hypotenuse. So if I type this in the calculator, I'll get exactly 100. Let me write it over here, and then I'll show you. So if I typed 200, I'll bring it closer to the screen. I don't mind this calculator, except the printing is smaller. So I could see that be a slight issue for you if I lay it on a table. So 200 cosine 60 is exactly 100. Now let's do the last side, the py. The magnitude of py divided by the hypotenuse, 200, is the opposite side over the hypotenuse, that is sine 60. So that means the magnitude of py is 200 sine 60. And that is approximately 200 times sine 60. That's not going to be a clean number. 173.2051 if you rounded it off that far. So 200 sine 60, and that's approximately 173.20508. Goes on forever. But now I know the length of this side. The length of this side is the 173.205. The length of this horizontal side is exactly 100. Now I can do the final length of the plane. I take the WY 15 and PY, and that'll be the length of this purple triangle. The plane's true speed with respect to the ground. Now I can't say 15 plus 173, stuff like that, because I didn't round off the 15. I could round this off where I like. They wanted 3 significant digits. But I'm going to type in this number and this number to the calculator and just physically add them. Remember, if the digits get crazy, you just let the calculator do the work. In fact, I can use the arrow key to go up here and get that number. 30 sine 30 that I want right here. And that, hit enter, put it down here on this line. Then I can go to the calculator and get 200 sine 60. Just arrow up, 200 sine 60. Well, first I'm going to add them, my fault, plus go up there and get that number, 200 sine 60. I do not want to type in the numbers. I let the calculator evaluate this right here. What do I get? I'm expecting to get 188 something. Okay, I got something different. So what did I do? I wanted 200 sine 60, not 200 cosine 60, my fault. So go back here to last entry, second function entry, and then I could change that cosine to a sine. Now let's try it. 188.205 stuff. But I'm going to say that this triangle here, I'm going to draw it small right here. 3 significant digits, 188. That's the vertical component of the speed. Now let's go for the horizontal component, which will be 100 minus the 2598. This length minus this length. And this length is the px. And this length right here was the wx, the horizontal component of wind. So let me take 200 cos 60 minus 30 sine 30. I could type it in. 200 cos 60 minus 30 sine 30. Now, what's the value of writing these numbers down as I work? So I know about what the answer is, right? I'm talking about 26 about and 100. What's 100 minus 26? About 74. So when I press this button, I better be seeing 74 about, or maybe I made an entry error again. 74, 85. Oh, they could like be almost close, but I don't like that at all. So let's go investigate that. What did I type wrong? 200 cos 60, got it. I was supposed to subtract 30 cos 30, and I subtracted 30 sine 30. So let's go back to second function entry right here. You see the word entry on this lower right-hand key. Let's go reclaim that thing I typed and change the cosine to sine to cosine. Okay, I didn't intend to make those errors. Now that's around 74 and change. I didn't intend to make those errors, but it shows you that I've got to keep track of everything. So this is about 74, approximately. Now I got to do one more thing. They wanted the plane's direction, so I need to know what that angle is. And that angle is the same angle as shows up here. So what am I going to say? I have the opposite side of that angle is the 74 and change. I have the adjacent side of the angle is the 188. That would be the tangent, 74 over 188. So if I use the inverse tangent key of 74 divided by 188, I will find that angle. Now notice, I'm not going to type in inverse tangent, and that's on the tangent key. Inverse tangent of 74 divided by 188. Let's find out what that is as an angle. About 21.4, 21.5 degrees. Why should I approximate before I'm finished? 74, 188, I got the true numbers right here. Let's do it with the true numbers. Tangent, go up there and get that 74. Divided by, saves you a lot of typing. Divided by, go up there and get that 188. Now I got the actual numbers in here. Is it going to make a difference in the answer? Maybe the difference is tiny, but maybe it's important. Let's check it out. Here the difference turned out to be tiny. 21.5, 21.5 either way. But if this had slipped below, then I would have had to answer 21.4. If that had been less than a 6, less than a 5, I'd say 21.4. Okay, so now I'm ready to give the final answer to the problem. Oh, wait a minute, I got to do one more thing. What's the magnitude of the speed? What is the length of that hypotenuse right there? Again, I'm going to use the Pythagorean theorem, but not square root of 74 minus 188. I'm going to take square root of these crazy long numbers, 74 and 188. Let's find out how long that is. Square root of, go get that number and square it, plus go get that other number up the screen and square it. Now I'm not rounding off at all. Do not round off at all in your preliminary calculations. Let's find out what that is. 202, 3 significant digits. I'll take 202 miles per hour. The plane did speed up, but only slightly. So the true speed and direction of this plane is 202 miles per hour. Okay, good. I'll get that, Victoria. Thank you. 202 miles per hour. And what was my angle? 21.4 from the north. I could call that north, 21.4 degrees east. Okay, thank you for the question, Victoria. So let me say, why did I square this? The length of this side right here is the hypotenuse of this right triangle. So I'm thinking, let's call that length C. I'm thinking square root of 74 squared plus 188 squared. I am going to use the Pythagorean theorem. C squared equals A squared, sorry, off the top, plus B squared. So I have to square the 74 and 188, but what I don't want to do is round off. So in the calculator, I went and got the full 74 and change. And I got the full 188 and change and squared them before I took the square root. So I was typing everything in once. That's a good question. Okay, so what's going on? No, the pilot is not going 30 degrees east to north. The pilot's actually going 21.4 degrees east to north. And how fast is her plane traveling? Not 200 miles per hour. That's what the engines are telling her. But relative to the ground, she's actually doing 202 miles per hour. Relative to the ground, people call that ground speed if you're a pilot. And what your engines are showing you, what your readings are showing you, is called airspeed. So her airspeed was 200 miles per hour, but her ground speed is 202 miles per hour. I don't know how many have flown in a plane, and I would say not very many times have I flown in a plane, and probably in the future, many less times, because this is so like traveling is messed up and plane tickets are expensive if you want to fly somewhere. What do you end up doing when you want to go somewhere? Oh, shoot, I'm just going to drive. Driving wears on you. But if it costs me $500 less, I'll take it. But what I'm saying is sometimes if you were flying an airplane, you know, the pilot's saying, okay, our speed in the air today is blah, blah, blah. And then you arrive 30 minutes late, you arrive 30 minutes early. How come they can't tell you when the plane's going to arrive? Well, because there's lots of variables like the wind speed and stuff. If the wind is helping you, you're going to go faster than you expect. You might arrive a little bit early. If the wind is fighting against you, then you might be slowed down slightly. You're going to arrive a little bit late. Okay. I like this and I don't like this problem. Here's what I like. You know, I try to show you every single step and carefully not rounding off too early. And how you add two triangles to make a third triangle. And I used their fancy vector notation you should get used to that. The thing that I don't like is I crammed it all on one sheet of paper. And so I admit that this is a little tight and hard to read. So remember, I'm going to scan this. You can look it up on our website later, but it gets a little bit busy and condensed on the paper here. I apologize for that. That's not ideal. You take it for granted what you would do if you were inside a classroom, and you could just go on writing on the whiteboard or the chalkboard without erasing or cramming stuff in. Okay, good. Now here's what we're going to do next. I need to bring you, this is the end of chapter 2. I need to bring you a little bit about terminology, and I'll foreshadow it right here to help you understand how to find the trig values of any angle, even if it's a crazy or not famous angle. So I need to show you a particular way that you read your calculator. And the words are reference angles and coterminal angles. So I'm not going to read this right now. It's going to take 5, come back, and I'll show you this diagram I've prepared for you. And then I'll show you how to use it when you got to find the values of real angles, like 11.3 degrees, or in some crazy direction, like, west of south or west of north. How do we talk about those angles so that everybody knows we're talking about the same thing? You'd be surprised now in math how critical it is that the numbers and the calculations, sometimes in the end, they're not the problem. The problem is you and me talking the same way. You clearly understanding someone. That actually turns out to be more a problem than pressing the right buttons in the calculator. You see in this problem, a couple times I pressed the wrong buttons. But because how I knew things were about how big, and I could see what I typed in the calculator, I could recover, say, oh shoot, I pressed the wrong button. But it's the language and the talking that sometimes confuses people when you and someone else aren't talking about the same thing. So let's just stretch your legs for 5 minutes. I got 124. Let's come back at 129, just to give you a tiny break there. And then I'll show you how to use your calculator effectively, what a reference angle is. So it's kind of summing up what we've done so far before we dive deeply into chapter 3. I'm just going to mute my microphone while we get up and stretch our legs. Okay, we're coming back here. So you've looked at triangles, you see how to read them, but you realize that sine, cosine, tangent, cotangent, and then later secant, cosecant, they're just talking about the ratios of the triangles. So if you type something into your triangle, into your calculator, I'm going to use the other calculator for a second, slightly larger screen. But if I type something like sine of 117 degrees, and then I type in something like sine of 73 degrees. I have to understand what these numbers mean. I have to understand what they mean in terms of a ratio. So let me just draw those two right here on the page. I'll bring it back over here, although it's kind of in the glare, isn't it? Remember, we always work from the horizontal, positive horizontal direction, and that's different than navigating, isn't it? People tend to always navigate from the north, but we describe angles in degrees always from the horizontal positive. So that if someone says north 30 degrees east, we have to be warned that I better start from the north. So 30 degrees is different than north 30 degrees east. 30 degrees is just above the horizon here. Anyway, this angle 117, what do we got? 0 degrees, 90 degrees, 180 degrees, 270 degrees. 117 degrees, that's 27 degrees past 90. It's this angle right here. And the sine is going to be the ratio. If that point is called x and y, and this distance is called r, we've learned to call the sine of 117 degrees the ratio of y to r. So when this says the ratio of y to r is 0.8910, let's approximate it as 0.8910. And you know what? If you're, that says 117, sorry. If you're just approximating a raw sine, cosine, tangent, cotangent value, 4 significant digits is usually as good as you need. So that's why I'm rounding it off right there. And the cosine of 117 degrees, let's find out what that is. Minus 45399. Now, if I round it off to 4 digits, I'd pop this 399 up to 4.0, minus 4540. Approximately minus 0.4540. And for that angle, 117 degrees, that's the best I can do. I don't know the exact value because that's not a famous angle. There's a famous angle nearby called 120, but I don't know better than this approximation from the calculator. That's all I have. That's why I need to learn to use the calculator. Now the negative comes from the fact that cosine is x over r, And in the second quadrant, the x values are negative and the y values are positive. The ratio of this length to this r is 0.450. It's a little bit less than half, whereas the ratio of this height to this r is almost 0.9, almost 9/10, almost fully the same height. So I can think of this as a right triangle, x and y and r. But I don't like to label the side of a triangle as to be a negative number, because that just gives me all kinds of problems, gives me a headache. I usually don't call lengths negative. You don't write a triangle like this and say the height of that triangle is 2, but the length of this side is -2. And then when someone asks you, why did you call that -2? You said, well, I was going to the left. No, the length of this is 2. The length of this is 2. That's a 45, 45, 90. So the length of this is 2√2. So I want to differentiate. I want you to make a difference between the full angle, 117, and this triangle that I'm going to draw here, which people call the reference triangle. If this is 117, then what's the measure of this angle right here? 180 minus 117, what would that be? 63 degrees. Let me clear the screen and write sine and cosine of 117 again. Again, crazy numbers that I cannot know for sure because this is not one of my famous angles. Now let's write sine and cosine of 63 degrees. Do you see that they're the same? Almost. Look at, I have to go up the screen. Sine 117 compared to sine 63. You know, those two numbers are the same. And that's a testimony to the fact that this height is the altitude or the vertical part of the 63-degree angle. And it's also the vertical part of the 117-degree angle. Y is positive, R is positive for both of these angles. But look at the cosine of 117 and the cosine of 63. Same number, but different sign. This one's negative, this one's positive. And what is that a testimony to? The cosine of 117 is negative because 117 is in second quadrant. And in that quadrant, x is negative, so x over r is negative. But just the raw triangle 63 degrees, I consider this length to be something I measure with a ruler. It's a positive number. So I am not going to, when I draw a triangle, write a negative number here because that represents a positive length. Well, if x and r were both positive, I would get the same number, but without the minus sign. Okay, what's the relationship between 117 and 63? It looks like the 63 would help us find the sine, cosine, tangent, and stuff like that because I could just read the triangle. But the sine and cosine of 63 are positive. The sine of 117 is positive, but not the cosine. So I'm thinking about this triangle as having the same trig values as 117. but adjusted for the quadrant I'm in. And this triangle, 63 degrees, is called the reference triangle of 117. It's the little triangle that's built on the x-axis. That's the complement or the supplement of 117. I take the 117-degree angle. I can't make a right triangle out of that directly. When I make a right triangle standing on the x-axis, I make an angle of 63 degrees. This is called the reference triangle. So let me show you how to use that. So when someone describes an angle to you, like 210 degrees, and 210 degrees is 30 degrees past 180, and they ask you for the reference triangle, what they're asking you for is the right triangle that you would build from that angle. It's based on the x-axis. And you only report that with positive angle numbers and positive links. Although the sine and cosine of 210 will be negative because both x and y are negative in the third quadrant. This red triangle, this reference triangle, you report all of those values as positive. Try it again. This is closer to the one I just said. If I give you an angle of 110 degrees, then the reference angle or the reference triangle is this triangle right here based on the x-axis with an angle of 70 degrees here and 20 degrees here. So the reference angle or the reference triangle is just the tiny triangle you build to support your angle. Build it on the x-axis. Never build a reference triangle on the y-axis. Never build a reference triangle over here. If you make a drawing like this, it's pretty much dead in the water. You can't use it at all. No flags. You always build a reference angle on the x-axis, whether it's above or below, you always build reference angle on the x-axis. Now, one more terminology. Because I could talk about 210 degrees, even if it has the same starting place as being 210 degrees, 30 past 180, or I could spin once around and come back to 210 degrees, I could add 360. That would be 210 plus 360 is 570. Or from the horizontal, I could go clockwise till I reach 210, and that would be called minus 150 degrees. Those concepts where I start and stop at the same place. I have the initial side on the positive horizontal axis and the terminal side on the same thing. It doesn't mean I want the same number of degrees. I could have spun around an extra 360. And that's what you get the scores for in the Olympics, right? Nobody wants to do a double axel. They want to do a triple axel. In snowboarding, that's skating. In snowboarding, you don't want to do a 180. You want to do a 540. What's a 180? Half circle. What's a 540? 1 1/2 circles. And of course, you go way, way past that. I forgot. They were talking about 1260s or something. I mean, 4 rotations, 3 rotations. They get out of control. Here, if I have an angle of 110, I could add another 360 to that and start and stop at the same place, but call that 470. 110 plus 360 is 470. That is coterminal. Or I could go clockwise backwards. 180 plus 70 more is minus 250. That's coterminal. So this is the first thing I need you to do is get this terminology straight. Coterminal is when your angles have the same starting position and the same terminal position. Same starting position on the positive x-axis, same terminal angle, but you might have thrown in or taken out a couple of full spins, a couple of full rotations. Add a 360, take out a 360, add two 360s, which is 720, take out two 360s. Coterminal means they're both in standard position, they both start at the same place, positive x-axis, and they both end at the same place. They both have the same terminal side. And the value of that is coterminal angles always have the same values for all 6 functions. But the reference angles are different. Whenever you draw a reference angle and label the sides, you always label the sides with positive numbers, both angles and sides. And you have to compensate if you want the sine, cosine, tangent of a full angle based on the reference angle. The sine, cosine, tangent, secant, cosecant, and cotangent will be positive or negative depending on what quadrant you're in. So let me do an example here for you. And this is not more than that. All I'm asking you to do is get used to the terminology. So let's say I've got sine of 117, and I've got sine of 63, cosine of 63, tangent of 63, cosecant of 63 degrees, secant of 63 degrees, cotangent of 63 degrees. If I ask the calculator what these numbers are, since I'm talking about an angle between 0 and 90, then I label all these sides, X, Y, and R, as positive, and all 6 of these will be positive numbers. But if I do sine, cosine, tangent of 117 degrees, 117 degrees, I apologize, I put this too close together, so I'm going to go down. Cosecant, 117 degrees. Secant, 117 degrees. Cotangent, 117 degrees. Even though that angle 117 is based off of a 63-degree angle, these numbers will be the same as the numbers here, but these might be plus or minus. In fact, the sign is going to be negative. I'm sorry, the sign is going to be positive because the sign is the y coordinate over r. Cosine is going to be negative. I can predict it ahead of time. The tangent is sine over cosine. Positive or negative is negative. Cosecant is 1 over sine, and reciprocal of positive is positive. Secant is 1 over cosine. Reciprocal of secant will be negative, and the cotangent is the reciprocal of tangent. The reciprocal of negative is negative. 4 of these puppies are going to be negative, even though they have the same values. Let's write them down. So I've already got sine and cosine, 8910, and I am approximating that I'll just take 4 digits. Cosine, 0.4539, well, 0.4540 if I round off. Positive. Tangent, 63. 19626. Now cosecant is 1 divided by sine. So 1 divided by sine of 63. I don't have a cosecant button. I just had to say 1 divided by sine. That's 11223. 1.1223. It's too crowded, I apologize. Secant, 1 divided by cosine of 63 degrees. You have to know your reciprocals. 2.2026, but round up, 2.2027. And cotangent is reciprocal of tangent, all approximating. 1 divided by tangent is 63, is 0.5095, and do not round up. 0.5095. Now come over here, you're going to see all the same numbers, but these people, sine and cosecant, will be positive, and these people, cosine and tangent, secant and cotangent, will be negative. Try it out. Sine 117, positive 8910. It's the same number I had a second ago, but the cosine of 117 is negative 45399, negative 4540. The tangent of 117, negative 19626. The cosecant, which is 1 over sine, 117, positive 11223. The secant of 117, which is 1 over cosine, positive, whoops, I didn't type 117, I typed 63. 1 divided by cosine 117, my fault. Yeah, see, same number, but negative sign. Negative 2.2027. And lastly, the cotangent is going to be negative. What was it over here? 5095? So before I press the button, I predict it's negative 5095. Now let's press the button. That was a tagline from a movie, an older movie. Maybe you haven't seen it. Press the button, Max. If anybody knew the movie that came from, I'd be really impressed, because it's a great, great movie. You should go rent it or watch it. It's just a comedy. It's funny. Negative 5095. These are all the same numbers. But when I talk about 117, I'm talking about the second quadrant. And so the sines, cosines, secant, tangent, cosecant, cotangent will be positive or negative depending on whether I'm using X or Y. And when I talk about 63, I'm pretending I'm in the first quadrant. And in the first quadrant, R, X, and Y are always, always positive. So all the ratios are always positive. The reason you like to have reference angles is because sometimes you have an angle that's more than 90 degrees or oriented differently, like in the airplane problem we just did. The headings, the adding of plane speed and wind speed. I just want you to be conversant with the terminology. So if someone asks you to draw a reference triangle, you draw it on the x-axis and you name that remaining angle. And if someone asks you to draw a reference triangle, then you name every angle and every side with positive numbers. One more example, because time's up, we got to go. Even if, let's talk about this. Let's talk about the angle, 310 degrees. Now, where is that? This is 0, but it's also 360. So 310 degrees is 50 short of 360. So 310 degrees is about like this. But the reference angle is this 50-degree angle, the leftovers. And even though this is below the x-axis, I don't call it minus 50. You always name reference triangles with positive number. If I was asking for the coterminal angle, you will say minus 50. That's the coterminal angle. But if someone's asking for the reference angle, you say 50. It's just a matter of terminology that you have to get used to. Okay, that's probably pretty good for today. Go ahead. And hang out. I got a couple questions privately. I'll answer them. But this is good for today. And then you can start to work on the next batch of homework. And in particular, go tackle that airplane problem on the written homework, because it's very much like this. I'm going to stop recording, but just this question that might be good for everybody. Written homework, we're giving you 2 ship courses and distances, and we're asking you for the distance from the origin. Shouldn't we just use the Pythagorean theorem to do the distance from the origin? And the answer is yes, after you've combined the right triangles. Because if you draw that really carefully, when you add the 2 ship courses, they do not form a right triangle. So you cannot directly use the Pythagorean theorem. Okay, if that's helpful. Yeah, you got to draw the 2 triangles that represent the 2 courses of the ship. And then you'll be on the right track. If you want another example that looks like this is not the way your homework looks, but look at this example in the book. This is example 5 on page 109. 2 vectors you're trying to add made out of 2 triangles, and you're going to add the components of both triangles in this picture. In the airplane problem we did earlier, we added one component and subtracted the other because the wind was blowing the plane back to the west. Okay, very good question. Thank you for bringing that up. But I am going to head out here, and you guys have a nice afternoon, and I'll see you next week.